This is our first video on transformers, and we'll be talking about transformers from an ideal perspective. Okay, we don't cover the non-idealness of transformers in this class. There is a course, EE 255, which goes over in great detail the non-idealness of transformers. Okay, but here we have the circuit symbol for transformer, and you can see that there's two inductor symbols separated by these two parallel lines. These parallel lines represent an iron core, which is typically how a transformer is made, where you take wire and you wind it around this common core. Okay, two wires that are wound around the same core. And there's two sides of a transformer. One's called the primary and the other's called the secondary. The primary is where you connect applied voltage. Okay, and transformers are AC devices. Okay, so your applied will be an AC type of source. And the secondary side is where you have induced voltage. Okay, so applied V over here and induced V over here. So transformers basically work on Faraday's principle, where when you put an AC source over on the primary side, well, the current, the AC current that flows through the primary winding develops a magnetic field that expands and contracts in time. The iron core there is there to strengthen that magnetic field, but the key aspect is that the expanding and contracting magnetic field induces a voltage through Faraday's law on the secondary side. Now you can see here the primary we're labeling V1 and the secondary we're labeling V2. There's a transformation equation, okay, that relates secondary voltage to primary voltage through the turns ratio. Okay, so secondary voltage is just equal to the turns ratio times the primary voltage, and the turns ratio N is a dimensionless number, which is just the ratio of the turns on the secondary side to the turns on the primary side. So N2 is what we're using to represent secondary turns, and N1 is what we're using to represent primary turns. So this ratio of the secondary turns to primary turns is the turns ratio. Now this is how the voltage is transformed from the secondary side, or excuse me, from the primary side to the secondary side. The secondary current is equal to primary current divided by the turns ratio. Okay, so you can see here that the secondary voltage, it's proportional to turns ratio, secondary current inversely proportional to the turns ratio. And in the ideal case, your primary power, okay, equals your secondary power. Okay, so that's why, you know, if your voltage, let's say N's greater than 1, well, if your voltage on the secondary side is greater than what's on the primary side, well, the current's got to be less by that same factor, because ideally, you know, these have to balance. You know, in reality, you're going to have less power on your secondary side than what you have on the primary due to losses, you know, internal to the transformer. But as I said earlier, in this class, we just consider the ideal case. Alright, so that's some basics of ideal transformers. The next thing we're going to cover, and by the way, these two equations together are called the transformation equations. Okay. The next thing we're going to cover is some common uses of transformers. One common use, and all transformers provide this, is isolation. And what we mean by this is that, you know, if we have two AC circuits, okay, here's an AC circuit, and here's an AC circuit. I mean, you can think of, you know, perhaps this AC circuit's a wall plug. I mean, you don't think of a wall plug as being a circuit, but wall plugs in your wall, they're all connected in parallel together, so it makes up a circuit. And then, let's say this is some sort of appliance, refrigerator or TV or whatever it may be, that gets plugged into the wall plug. Well, one way to do that is, of course, just directly connect with two conductors. Okay, this would be an electrical connection. Okay, but often when you have two AC circuits, I'll draw it like this here. Actually, let's go to the next page. Okay, and I'm going to draw below here. So these are the other uses, transformation and impedance reflection, that we're going to get to later. But still talking about isolation here. So one way to connect up two AC circuits, like I showed on the previous page, is an electrical connection. Just take two conductors, two wires, and connect the circuits directly. Okay, but often what we'll do instead of an electrical connection is we'll provide what's called a magnetic couple. And what that means is that in between the two AC circuits we put a transformer. Right, so you see this is magnetic couple. And you see the reason why this is often done is because now you see the AC circuit here, let's say this is the wall plug again. Okay, and here's our appliance. So you see the appliance is connected to the induced side of the transformer, the secondary side. The AC circuit, the wall plug, that would be our primary side. Primary here, secondary here. So you see, if something catastrophic happened to this appliance, like say, it's a TV and somehow water gets inside, which is bad. Anytime, water and electronics do not mix. Water would cause short circuits, which would cause more current to flow than, what the components could handle, and, worst case, you can get a fire. So if something were to catastrophically happen to this appliance here, well, putting the transformer in between, it saves this circuit, that the wall, in this case the wall plugs, would not be damaged. In all likelihood, you put water in an appliance like a TV and this is gonna basically fry, but that transformer provides protection to this AC circuit, the wall plug, where if you had made a direct connection, okay, an electrical connection with two wires like this, well, if something catastrophic happens to the appliance, well, it's going to cause a catastrophic failure to this other circuit, which, if it's a wall plug, it could start a fire in your wall. So transformers provide, a layer of protection. Okay, so all transformers provide isolation, and that's one of its big uses. Now, transformers also provide transformation, and this comes from what we discussed earlier, that the secondary voltage is transformed by the turns ratio, okay, in a proportional way, and the secondary current is transformed by the turns ratio in an inverse manner. Okay, again, N is the turns ratio. Okay, the ratio of secondary turns to primary turns. So a transformer has the ability, depending on this N value, whether it's greater than or equal to 1, of building up voltage, that the secondary voltage could be bigger than the primary voltage, or vice versa, and same thing with the current. But as we discussed earlier, since primary power and secondary power, okay, in an ideal transformer are the same, if the voltage on the secondary side is greater than the primary side, well, the secondary current has to be less than the primary current, okay, to get this balance. And then impedance reflection, this is a use of a transformer where if you have two impedances, we talked about in an earlier video that if you want maximum power transfer to an impedance load, okay, say this is the S here, and this is the L. Well, we learned in a previous video that to get maximum power transfer, you want the load impedance to be the complex conjugate of this impedance here. Well, sometimes due to design constraints, it's not possible to directly get the load impedance to be the complex conjugate of this impedance here. But what you'll see, and there's a whole video that we're going to discuss this, but what you'll see is that a transformer has this property of impedance reflection where I can use a transformer in between these two impedances and get a match between the load impedance and the source impedance where I otherwise would not be able to. Okay, so impedance reflection has to do with making a match. Remember, we called this a match. Okay, a match between a load and a source, right, for maximum power transfer. So you'll see transformers have the ability, due to this property of impedance reflection, to make a match where it wouldn't otherwise be possible. Okay, and like I said, we're going to have a whole video dedicated to this. Okay, lastly in this video, I just wanted to go over the types of transformers. Okay, there's 3 basic types and then one other type I want to talk about. There's a transformer that's called step-up. Okay, and step-up transformers have a turns ratio greater than 1. Okay, which means that its secondary voltage is greater than its primary voltage, and its secondary current, it's a tilde, is less than its primary current. Okay, there's step down. Okay, step down has a turns ratio less than 1, and it's just the opposite of what we had here. The primary voltage is going to be greater than the secondary voltage, and the secondary current is going to be more than the primary current. Okay, that's step down. Then you have isolation transformers. Isolation transformers. Now, you know, as I said just a little while ago, all transformers provide isolation. So, you know, step up, step down, and any other transformer provides isolation. But you see, there's these transformers where the turns ratio is equal to 1. So, you know, your secondary values and your primary values are the same since the turns ratio is 1. So you see, isolation transformers, you're strictly using the transformer for isolation because you're not using it for the transformation of the voltages or currents. So that's where the name comes from. And then the last transformer I just want to briefly discuss is that there's transformers that are called center tapped. Okay, and what a center tapped transformer is, and I'll draw the symbol here. Okay, symbol looks just like a non-center tap transformer, except there's an added connection on the secondary side. Okay, this is your primary here, and this is the secondary. So, you know, let's say I put an AC source. Okay, I don't know, let's say it's let's see, we can say it's a 120 volt source, and you know, let's say the turns ratio is 3. Well, on the secondary side between the 2 outer connections, or we'll put it over here. Okay, since we have a turns ratio of 3, our secondary voltage is going to be 3 times the primary voltage, which is 120, since this source is connected directly up to the primary. And that's across the outer 2 contacts of the transformer. Right, so that'd be 360. But you see, between either outer contact and the center tap contact will get half the total of the secondary. So you see this would be 180 and this would be 180. So these center tap transformers provide a voltage division aspect to the transformer on the secondary side. There's also transformers that have multiple taps instead of just one center tap. You can get transformers, sometimes the secondary will have 6, 7, 8 or more wires coming out of there where they've been strategically placed to divide up the voltage in a particular fashion for a particular design. Alright, well, this was some basics of transformers, the basic operation, their uses, and the different types. Next video is going to be dedicated to talking about impedance reflection, and then we'll do an example showing how we can make a match with the transformer's ability to do impedance reflection where we otherwise wouldn't be able to make a match.